All right, let's tackle a huge idea in modern math, topology. Now, I know that word might sound a little intimidating, but I promise you, at its core, it's all built on just a few super simple and pretty elegant rules. So let's just dive right in.
So this is the big question, right? What is a topology? By the time we're done here, you're going to be able to answer that no problem.
Okay, to get started, we really only need two things. Think of it like you're about to cook something. You got to get your ingredients together first.
And you might be surprised by just how simple these ingredients are. First up, we need a set, and we're going to call it X. Seriously, just think of it as a bucket of stuff. Could be numbers, letters, you name it. Second, we need a collection, which we'll call by the Greek letter tau, pronounced tau. Now, this is just a specific handful of smaller groups, or what we call subsets, that you can make from the stuff inside X. And that's it. A set X and a collection of its subsets, tau. That's all we need.
So now that we have our ingredients, we can finally get to what a topology is. And really, it's just a game with three essential rules. If our collection, tau, follows all three of these rules, then, boom, it's a topology.
Let's walk through them. Rule 1 is the easy one. Our collection tau has to contain two specific things: the empty set, which is just a set with nothing in it, and the entire original set X. Got it? Good. Rule 2, the union rule. This just says that if you take any of the groupings from your collection tau and merge them together, the new group you get has to also be in tau. And finally, Rule 3 is almost the same. If you take any finite number of groups from tau and find only what they have in common, their intersection, that result also has to already be in tau. If it breaks even one of these rules, it's a no-go. It's not a topology.
Okay, enough with the abstract stuff. Theory is great, but let's make this real. We're going to grab an actual example and see if it can pass our three-rule test. So, here's our setup. Our set, X, is just the three letters A, B, C. Simple enough. And our special collection, tau, has exactly four things in it: the empty set, the set with just A, the set with AB, and the whole set, ABC. So the big question is this collection tau a topology on X? Let's find out.
First things first, let's check rule number 1. Does our collection tau include those two must-haves, the empty set and the entire set X?
Yes, it does. We can see it with our own eyes. The empty set is right there, and so is the full set, A, B, C. So far, so good. Rule 1 is a check. Okay, on to the next one. What about the union rule? If we start smushing together any of these four sets in our collection, is the result always going to be one of the other sets already in the collection? Let's try a few. What if we combine A with AB? Well, that just gives us AB. Is that on our list? Yep, it is. Perfect. How about we take the empty set and combine it with A? That just gives us A, which is also in our collection. And it turns out, no matter which ones you combine, you always end up with something that's already in tau. So that's another big yes. Rule 2 passes. The fancy math term for this is that the collection is closed under union. It means you can't escape the collection just by combining things. We are on the home stretch now. Time for the last test, the intersection rule. If we look at what our sets have in common, do we stay inside the collection tau? Let's check it out. What do A and AB have in common? Well, just the letter A. So the result is the set A. And is that in our collection? It sure is. What about the intersection of AB and the whole set? Well, that's just AB, also on the list. And yep, you guessed it. Any intersection we try lands us right back inside our original collection. And that's it. 3 for 3. Our little collection T has passed every single one of the tests. So what does this all mean? We put our example through the ringer, and it passed. And in doing so, we've kind of unlocked the official language to talk about this stuff. This is the moment. Because our collection tau followed those three specific rules for our set X, we can now officially say that tau is a topology on X. That's it. That's the definition we've been looking for. And there's just one more piece of lingo. When you take your set X and a topology tau that you've built on it, and you think of them together as a pair, That whole package is called a topological space.
Now, let's learn how to speak the language like a mathematician. Those individual things inside our original set X, our A, B, and C, from now on, we call those points. And those special subsets that made up our collection tau, the ones that passed all our rules, we call those open sets. So really, a topology is just a special collection of open sets that plays by our three rules.
And this brings us to the really cool mind-bending part. Think about what we just did. We've defined a kind of structure, a way of thinking about shape and what's close to what, using nothing but a list of groups and three rules. We didn't use a ruler, we didn't measure a single distance. So the real question becomes, if you can define space in this incredibly flexible way, what new kinds of universes does that let you explore? That right there is the power of topology. Thanks for joining me.